Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and we're going to be talking about something called the thermal wind. It's sort of a hypothetical type thing. It really doesn't exist in the atmosphere. It's more of a mathematical and physical concept, but it does help to explain some things. And basically, one of the things you can do with this is take a look at how the winds change from one level of the atmosphere to the next in direction, and that can tell you whether or not you're either bringing in cold air or bringing in warm air. So that's what we're going to be delving into here in just a little bit. In fact, right now. All right, so let's have a hypothetical situation where the winds near the ground are out of the northwest at 15 miles per hour, and the winds at about 5,000 feet are blowing from the southwest at 45 miles per hour. Okay, so northwest near the ground, southwest about a mile up. Now, in order to talk about this, we have to do a little bit of review on vector addition, okay? And for those of you that don't like math and don't like vectors, it may be time to go grab a Miller Lite at this point. But here we go. If we have one vector, we're going to call it vector A, and we then have another vector, vector B, and we add those two, then this is the resultant vector, which we're going to call C. So you line up the beginning of the second vector with the end of the first one, and then you connect the end of the first one to the end of the second one. I'm sorry, the beginning of the first one to the end of the second one, and that is your resultant vector. Okay, so that's how you add vectors. Okay, so what is the thermal wind? Well, it turns out that the lower level wind vector, which in our hypothetical case here is southwest is northwest at 15, plus the thermal wind vector is equal to the upper level wind vector, okay, which in this case is southwest at 45. And think of the thermal wind as an isotherm, or a line of equal temperature in the layer from the low level wind to the high level wind, okay? So in a sense, it's sort of telling you what the amount of vertical wind shear is in that layer. So back to our example. We've got our northwest wind at 15 near the surface, southwest wind at 45 at 5,000 feet. Now, in order to find out what the thermal wind vector is, remember, we have to add the thermal wind vector to the low-level wind vector, which is this one here, okay, to get this one. So we line up the ends, or the beginnings of both of them, and then our resultant vector, the thermal wind, is this, okay? So here's our low-level wind vector, northwest at 15. We're adding the thermal wind vector, which is this, and then our resultant vector is the wind in the upper atmosphere, which is southwest at 45. Now, cold air is always to the left of the thermal wind. So the thermal wind is blowing this way. This is sort of our isotherm, if you will. So cold air is going to be on the left of that thermal wind, okay? And if you take a look at both the winds near the surface and also at 5,000 feet, they're both blowing from cold air to warm air, okay? And so we call this cold advection. And the winds, in this case, are backing with height. Now, what do I mean by that? Well, it means that the wind direction is turning in a counterclockwise manner. So it's starting off northwest, and then it's turning around to the southwest. And whenever you have that, that means you have cold advection going on between those two levels, okay? So if the wind is backing with height, turning counterclockwise, then that means that you've got cold air moving in to that particular layer, okay? I hope that makes a little bit of sense. Now let's go on to example 2. Here, instead of having a northwest wind at the surface and going to southwest aloft, we're going to do a southwest wind at the surface and a northwest wind at 45 aloft. So notice here that the wind is not backing with height, it's doing what we call veering with height, where it's turning clockwise. It's starting off southwest, and then it's turning like this into the northwest as you go up, okay? So why is that important? Well, let's do our little vector project here again. We're going to line up the beginnings of them, because remember, this is the low-level wind vector up in here, southwest at 15. We're going to add the thermal wind to that vector, and our resultant vector will be the wind at 5,000 feet, which is northwest at 45. Now remember, thermal wind is now blowing this way, and cold air is to the left. Okay, so there's the cold air. And notice that both of these arrows are blowing from the warm air toward the cold air. Okay, now, yes, it's true that cold air is more dense than warm air, and if it doesn't want to leave, it's not going to. But in this type of situation, we call this warm advection because the air is blowing from warm air toward cold air, and the wind is veering with height or turning clockwise in direction. Okay? So the basic conclusion out of all this mess is the fact that if you take a look at the winds at two different levels of the atmosphere, and you see how the wind direction is changing from the lower one to the upper one, it will tell you whether or not that layer between the two is getting colder or getting warmer. If the wind is backing with height or changing direction in a counterclockwise manner, you have cold advection. If they're veering with height and they're turning, the wind direction is turning clockwise as you go up in the atmosphere, then you have warm advection. Okay, or warm air moving in. So that's the basic nuts and bolts of it. And if you look, when they send the weather balloons up, what you'll see a lot of times is that there'll be cold advection in one layer, warm advection in another one. In fact, if you think about it, in the summertime, if you have cold advection up there, or even in the spring, maybe even more likely in the spring, if you have cold advection up there and warm advection near the surface, then it's going to become more unstable. The lapse rate of temperature will become more extreme because it's warming up down here and getting colder up here, okay? So the lapse rate is getting very, very steep. In the wintertime, sometimes you'll have cold advection right near the ground, like maybe a big high over New England, and it's driving that cold air down the east slopes of the mountains. But up there, there's warm advection going on, okay? So the wind would be backing with height near the ground, and then as you go up in the atmosphere, then it would start to turn around and go the other direction and start to veer with height, and that would make the atmosphere very, very stable. It probably gives an inversion, okay, where the temperature actually increases with height. Okay. I know I probably pushed this a little bit more than I normally do it, but I hope at least some of this made sense, or at least the bottom line of all of it makes sense. So that's bonus weather video number 2 for today. We'll have another one for you coming up next Tuesday. The daily weather update will be posted within seconds of the time that I stop talking here. And that should be about it until Monday, okay? And again, just to remind you, going to be at the Panera Bread, Glenwood Avenue, 6100 Glenwood Avenue in Raleigh from 2:30 to 4 tomorrow. If you get a chance, if only briefly, stop by. We'd love to see you and be able to say hi. Have a great weekend, everybody, and we'll talk to you soon.